Okay, Chapter 0, Section 7, Rational Expressions. Okay, in this section, we're going to cover the domain of an algebraic expression, simplifying rational expressions, multiplying and dividing rational expressions, adding and subtracting rational expressions, compound fractions, rationalizing the denominator or the numerator, and then avoiding some common errors. Okay, rational expressions. A quotient, right, which is a fraction, of two algebraic expressions is called a fractional expression. Here's some examples. Okay, so we have, maybe these should be kind of comma separated so they don't look like something, so they don't confuse you. So this should be one example, another example, another example, a fourth example. Okay, so we're looking at fractions where the numerator and denominator have these sort of complicated statements. They could be polynomials, or they could be something like this, root, right? So they're complicated fractions. A rational expression is a fractional expression in which both the numerator and denominator are both polynomials. For example, the first three expressions in the above list are rational expressions, but the fourth is not, since the denominator contains a radical. Okay, so of these four examples up here, this one does not fit the form of a rational expression because it's got this giant root in the denominator. Okay, so the first three are examples of rational expressions. So in this section, we're going to learn how to do algebraic operations on rational expressions, such as adding, multiplying, dividing, and so on. The domain of an algebraic expression. The domain of an algebraic expression, in general, just means that we're going to figure out the set of numerical values that can be substituted for the independent variable in the given statement and have a valid answer, a valid solution. So there's two main things we really have to focus on. We're not allowed to divide by 0 is one of them. And two, we're not allowed to take the even root of a negative number, because if we did, well, I shouldn't say we're not allowed to. It's just that when you take the even root of a negative number, that leads to an imaginary. And so in general, we want to stick to real numbers, not imaginary numbers, unless you're told that you're allowed to go into the complex number system. Okay, so by default, we're talking about real numbers, and so you have to be careful about those two situations. Right, so for this first example, 1 over x, we have to think ourselves, what can x be? Right, so let me come back over here. So if we have 1 over x, we can say, well, the x is allowed to be a 2. Yeah, if we have x equal to 2, if x equals to 2, then this will lead to 1/2. And that's okay. That's a valid answer, right? On the other hand, x cannot be equal to 0. If x equals to 0, then we'd have 1 over 0, and that's not allowed, right? Not allowed to divide by 0. So when we talk about the domain, very often what we do is really think about the things you're not allowed to have and then say, by default, everything else is okay. This style of notation expresses that for us. So this is set builder notation. What we do is do the wiggly brackets on the edges, and then we write down the variable type, in this case, the x. This line, this bar reads such that. So when you read this, you say the answer is x such that, and then you put a condition over here. The condition is simply that x is not equal to 0, right? So by default, it could be anything else as long as x doesn't equal to 0. So that's how you express the domain of this value. It could be anything except not 0. Okay, for this expression, for the square root of x, okay, so now we can't divide by 0. There's no fraction in the statement, but we do have a root, and by default, the little index there, which is missing, remember, by default, if there's nothing there, that means there's a little visible 2 right there. So this is the square root. The square root is an even root, which means that if we try and take the even root of a negative number, we'll end up with an imaginary, right? This is equal to an imaginary number I. So again, by default, we try and avoid those unless you're specifically told that you're allowed to or that they want a complex number solution. Otherwise, we stick to the real numbers. And so we want to avoid that, right? So again, this is allowed to be anything as long as it's not negative. It's allowed to be 0. It's allowed to be 1, 2, 3, right? It could be a whole number, a fraction number, anything as long as it's positive. And again, that's what this set builder notation is describing for us. It's x such that, and then the condition, and the condition is that x is greater than or equal to 0, right? As long as there's no negatives. Good. Okay, and then we can have sort of a combination of the two, such as this third example. So now we have this third example over here, where we have a fraction and we have an even root. So we have to think about both situations and provide the list of numbers that doesn't offend either one, right? So in terms of the fraction, we know we're not allowed to divide by 0, and I know that if x equals to 0, then we have the square root of 0, which is 0, right? The square root, the square root of 0 equals to 0. So in terms of the root, 0 is okay. There's nothing wrong with 0. However, when we have 1 over the square root of 0, well, this leads to 1 over 0, which is not allowed. Okay, so because of the fraction, x equals to 0 is not allowed. And because of the root, we know that x must be a positive number. And so now the domain is x such that x is strictly greater than 0. Right? So the only difference between these two is that here 0 is allowed because you can take the square root of 0. That just equals to 0. But here in this set, we want them to be all positive, and we do not include the 0 because of the fraction. Okay, let's look at a couple of examples. Okay, so let's take a look at a couple of examples. First one, let's say we're given 2x squared plus 3x minus 1, and we're asked to find the domain. So if we look at that, we have to think to ourselves, is there a value of x that would result in us dividing by 0? And there isn't, because there isn't a fraction there, right? So x can be anything. It could be 0, it could be negative, it could be positive, and you're never going to be dividing by 0. The other thing to think about is that you can't take the even root or the square root of a negative number, and again, there are no roots here. So for the first one, the domain is all real numbers, right? You're allowed to plug in anything you want. The domain is all real numbers. For part B, it gets a little bit more complicated. We have x divided by x squared minus 5x plus 6. So clearly a giant fraction, so we have to be thinking, are we dividing by 0 somehow? So we have to think to ourselves, what value of x can would result in a 0 in the denominator, right? So very importantly, it's not that x cannot be 0, it's that the fraction itself cannot have a 0 in the denominator, right? So 0, x equals to 0 is fine. If we let x equal to 0, we simply get 0 divided by, right, if x equals 0, we just end up with 0 divided by 0 squared minus 5 times 0 plus 6, which just gives us 0 divided by 6, which just equals to 0. So that's perfectly okay. 0 is a valid result. What we can't have is something in the denominator that results, a value of x in the denominator that results in a 0. To figure out what that is, we need to factor the denominator. So this is a trinomial. The coefficient in front of the x squared is a 1. So we just simply need two numbers that multiply to 6 but add to negative 5. So 2 and 3 work out. 2 times 3 is 6. and we need them to be negative, so negative 2 and negative 3 work out. Okay, so we factor out the denominator. We end up with x minus 2 times x minus 3 in the denominator. And now in this factored form, we can easily tell what values of x would result in a 0. Because if we let x equal to positive 2, or if we let x equal to positive 3, in either case, we end up with a 0 in the denominator. Right? So for instance, if x equals 2, we end up with 2 divided by 2 minus 2, 2 minus 3. Right? And this is the case where I've taken every x value and replaced it with a 2. 2, 2, 2. Right? And so obviously this would be a 0 times a negative 1, so we get a 0 in the denominator. On the other hand, if we come over here and instead we replace the x with a 3, put a 3 there, put a 3 there, put a 3 there, and put a 3 there. Now this is the case where I've replaced each of those x values with a 3, and now we get a 0 from this term, and so we end up with a 0 in the denominator, and that's how we're going to be dividing by 0. So we're not allowed to have a 2 or a 3. So the domain is simply to state x is allowed to be any number at all, except x is not allowed to be a positive 2, and x is not allowed to be a negative 3. I'm sorry, positive 3. So that's what this statement down here is indicating. X such that x doesn't equal the x does not equal to 2, and x such that the domain is x such that x does not equal 2 and x does not equal to 3. Good. So by default, everything else is fine. It's just identifying the things you're not allowed to have. Okay. Looking at the third case, now we have kind of a mixture of things. We have a root and we have a fraction, so we have to take both things under consideration. From the root part of it, we know that we cannot take the square root of a negative number, so x is not allowed to be negative. So from just looking at the root part, x should be greater than or equal to 0. Good. And in the denominator, we're not allowed to divide by 0, so x is not allowed to be 5. And so that becomes our two conditions. Right? So the solution to this is the domain is all real numbers, right? Except the case where it's negative and the case where it equals to 5. So here's how we write that down in set builder notation. It's x such that x is greater than or equal to 0 and x does not equal to 5. These are the two conditions that we have to keep. Okay, so when you're finding domains of rational expressions, you just have to think about those two things. Don't divide by 0 and don't take the even root of a negative number. It's easier to find the things you're not allowed to plug in and then say by default everything else is fine. Okay, simplifying rational expressions. Okay, first we're going to look at cases that fit this form. Situations where we have a times c divided by b times c. And so what we're going to do is we're going to cancel out that common term of c. Right? So here, notice that we have a multiplication by default. If there's no other operational symbol between two things that are clearly distinct, then by default we know that there's a multiplication between them. So this is a times c divided by b times c. And so now in this case, the c's cancel to give me just a over b. Okay, so those are the first kind of case we're going to look at. For example, say we're given this. Simplify by cancellation. All right, well, very important. You're not allowed to cancel when there's addition or subtraction. Very common mistake. So we're not allowed to say, well, let's just cancel that and cancel that. And the answer is negative 1 over x minus 2, right? That's not true. Doesn't work that way, right? So we can only cancel when there's multiplication, not when there's addition or subtraction. So the tricky part of this whole thing is that we have to figure out how to rewrite it as a multiplication, if possible, and then maybe we can cancel some things. So step one is going to be to factor everything. All right, luckily these aren't too bad. For the numerator, we have an x squared minus 1. I'm going to put that off on the side over here. X squared minus 1 is the same thing as x squared minus 1 squared. This is a difference of squares, right? So this is going to be x plus 1, x minus 1, just from our patterns of common factors. Okay, the denominator, on the other hand, that one is x squared plus x minus 2. Going through my list of factoring techniques, okay, they don't have anything in common. There's no common letters or numbers. Factor by grouping wouldn't work because there's only 3 terms. This does not fit any of my patterns, so nope, no way to simplify that. And so we're going to have to do factoring of the form x squared plus bx minus c, or plus c, sorry. So this is a trinomial with the leading term is a 1. So this is the case where we're just looking for 2 numbers that multiply to -2 but add to positive 1. So not too bad. We can just kind of guess and check a few things. -2, so there has to be maybe a 2 and a 1. Those 2 numbers multiply to give me a 2. And I want it to be positive 1 when I add them, so maybe make it plus 2 minus 1. Right, so that works out. Good. Okay, so now let's come back over here. So now we can come back over here after we've done our factorization. And so the numerator can become x plus 1 times x minus 1. And the denominator becomes x plus 2 times x minus 1. Good. Now we have multiplication. Now we're allowed to cancel. And again, we're not allowed to cancel the individual things. So I can't cancel this x and this x. I can cancel the whole binomial, right? Because it's being multiplied. So this entire binomial is identical to this entire binomial. So we can cancel them. In practice, we just cancel them. But just this one time, I just want to make sure it's clear why we're allowed to cancel them. So I'm going to take a couple of other steps and rewrite it this way, since we have that. Remember that when we have multiplication, we do not need a common denominator to combine or separate fractions. So I'm going to rewrite this as 2 separate fractions, x plus 1 divided by x plus 2 times, and then I'll put the x minus 1 over the x minus 1 over here, right? So if I was asked to multiply these 2 fractions, again, you don't need a common denominator, so I would just multiply the numerator, multiply the denominator, and I would get to there, right? Now here, this is a new version of 1 because we have a fraction where the numerator and the denominator are identical. So this is x plus 1 divided by x plus 2 times, and this whole thing just becomes a giant 1. And 1 times anything is the same value. It doesn't change. So then this becomes x plus 1 divided by x plus 2. Okay, so people usually just skip these 2 steps right here. But that's something you should have in mind, that that's the reason why it works, right? Mostly people just come over here and they just cancel these 2 things and then jump to rewriting it without that and say that this is x plus 1 divided by x plus 2, right? But this is sort of the logic for why it's true. All right, so that's not too bad. Here's the solution provided by your author. Similar, factor the numerator, factor the denominator, cancel out the common factor, and there you go. So factor everything, cancel. Multiplying and dividing rational expressions. Okay, so now we're going to be looking at cases that fit this form. We have one fraction multiplied by another fraction in this form. And so we just multiply the numerators, multiply the denominators like this. Again, when we're multiplying fractions, we do not need a common denominator. So these should be fairly easy. Let's look at an example. Say we're asked to multiply these 2. Well, it's true that we could literally just multiply them and you can have polynomial multiplication. So this is equal to this multiplication here. So let me go ahead and I could put parentheses around these guys. I'm multiplying, and and then I could do multiplication on these, multiply this times this, and this times this, and then this term, right? So this could be equal to 3x cubed plus 12x squared plus 6x squared plus 24x minus 9x minus 36, and then that whole thing gets divided by the denominator, which again we're going to take turns multiplying. So x squared times x is x cubed minus x squared, and then 8x times x gives you plus 8x squared, 8x squared, 8x, and then plus 16x minus 16. Okay, and then we would combine some like terms, right? So then in the numerator, let's see, these two are like terms. And in the denominator, these two are like terms. And in the numerator, again, these two are like terms. And these two are like terms. So this simplifies down to 3x cubed plus 18x squared plus 15x minus 36 divided by x cubed plus 7x squared plus minus 16. So while that's technically correct, we are expected to always provide the simplest answer. So now we have to simplify this. We'd have to factor this whole thing out in the numerator, factor out the denominator, and cancel when appropriate. In general, this process is going to be more difficult than it needs to be. There's an easier way to do this. So even though this is technically correct, we don't really want to do it this way. Instead, we want to invest some time into factoring these things first. Factor out all four terms as much as possible, and then you can cancel, if possible, cancel some stuff. Often something in this section, your author has very carefully chosen some values where some stuff usually cancels out nicely, and so you'll find that life is just a little easier that way. So let's factor out each one of these things. So x squared plus 2x minus 3, x squared plus 2x minus 3. This is a trinomial. Leading term is 1. We need two numbers to multiply to -3, but add to +2. A little guessing and checking should lead us to the right answer. 3 and 1 is necessary to multiply to 3, but we need it to be negative, so one of them is negative, and I need that to be positive. So make that a plus, make that a minus, and that'll give us the values we need. Okay, so that's how we factor this numerator. Okay, next we got to factor the 3x plus 12, and well, they only have a 3 in common, so we can just factor that out as 3 and then x plus 4. Good. This one equaled that one. And then x squared plus 8x plus 16. Again, this is a trinomial. Leading term is a 1, so we just need two numbers to multiply to 16 and add to 8. Also, if you notice, this also fits one of our patterns, though, because it's true that this is the following. The first term is squared, the last term is squared, and the middle term happens to be twice the two things that you squared, x and a 4. This is going to be x plus 4, parentheses, squared. Good. Something squared there. So you can do guessing and checking and confirm that this actually does fit that. Okay, so now that we have all three pieces, well, the fourth one doesn't simplify any further, right? X minus 1. So we have the first one, highlight it right here. This is going to become this. and this one is going to become this one, and this one is going to become this one. Okay, so let me substitute all that in there. So our new product is going to be equal to x plus 3 times x minus 1 times 3 times x plus 4, the whole thing divided by, and we have an x plus 4. I can write it as an x plus 4 squared, but I'm just going to copy it twice since it'll make it neater when I cancel. And then there's a copy of x minus 1 there. Okay, so now everything is being multiplied, and so we're allowed to cancel. And so x plus 4 and x plus 4 cancels, and x minus 1 and x minus 1 cancels, and nothing else does. So now we just write down the survivors. We end up with 3 times x plus 3 in the numerator. It's the only thing that survives. And then the denominator, the only thing that survives is an x plus 4. And so now as a final step, I'm just going to go ahead and distribute that 3. And so our final result is going to be equal to 3x plus 9 divided by x plus 4. Okay, so this is our final result. And we would have gotten the same answer had we done it this way, multiplied it all out, expanded it all out, combined like terms, and then factored. It's just that going from here to here is hard work. Hard work. Possible, but very hard. So why do it that way? Okay, so the lesson we should learn is before you jump into multiplying, the first thing you should do is factor everything. Things will reduce, cancel nicely, or they often do. And then you have something that's a lot simpler to work with. Here's the solution provided by your author for the exact same thing. So it's the same work. Factor out each term. And yeah, so exactly the same way I just did it. Okay, multiplying and dividing rational expressions. So now we're going to work with cases that fit this form. A over B divided by another fraction, right? So we have one fraction here divided by, we're going back to this division notational symbol, another fraction. So this is the same thing as having A divided by B divided by C divided by D, right? So we have one fraction divided by another fraction. We're just using this notational symbol there to represent that. Okay, and so we're saying that this is equivalent to this. A over B divided by C over D is equivalent to A over B times D over C. We multiply the first fraction times the reciprocal of the second fraction. Okay, I think people also memorize keep, change, flip. Keep the first fraction, change the division to multiplication, flip the second fraction. Keep, change, flip. Okay, hopefully this looks familiar, but this is what we're going to work with, and this is what's going to help us simplify rational expressions that fit this form. For example, say we're asked to simplify this, right? So we have, again, one giant fraction where the numerator is this whole thing here, right? So this whole fraction is in the numerator divided by this whole fraction over here. Okay, so we're going to keep the first fraction and multiply it times the reciprocal of the second fraction. So we're going to rewrite it as x minus 4 divided by x squared minus 4 times, and then we flip the second fraction, which is going to be x squared plus 5x plus 6 divided by x squared minus 3x minus 4. Okay, so that takes care of this. That's all we had to do to get rid of this division symbol. Multiply the first fraction times the reciprocal of the second fraction. And so now this just goes back to the previous situation where we have to simplify this. And to do that, we're going to factor each term. So let's do it right underneath it. This is going to become a difference of squares, right? So this is going to become x plus 2, x minus 2. That takes care of this one. This one is already simple, as simple as it gets. What about this one? So we have a trinomial. Leading term is 1. So we need two numbers to multiply to 6 and add to 5. That's not difficult. So this one turns into x plus 3, x plus 2. Right? Guessing and checking will confirm that that's the way that factors. And finally, we have this one. So again, a trinomial, leading term is 1. So I know that I need to find two numbers that multiply to -4, but add to -3. And again, simple numbers, so it's easy to guess. Let's see, we need a -4 and an x plus 1. Right? And again, guessing and checking confirms that that has to be the way that factors. Good. So I'm just going to copy everything again. So we have an x minus 4 there. And then in the denominator, this turns into an x plus 2 and an x minus 2 times. And then in this numerator here, we end up with an x plus 3 times an x plus 2. And then in this denominator, we end up with an x minus 4 times an x plus 1. Okay, again, everything is being multiplied. Multiplied. So now we're allowed to cancel. The x minus 4 cancels with x minus 4. And x plus 2 cancels with x plus 2. And so now there's only 3 survivors. There is a x plus 3 in the numerator. And there's an x minus 2 and an x plus 1 in the denominator. So let's write those down. And so this turns into x plus 3 in the numerator, and in the denominator is an x minus 2 and an x plus 1. So this is a perfectly good solution, leaving it like that. But also we might want to FOIL that out to get a polynomial in the denominator. So x plus 3 divided by x squared, and then x times 1 is x, minus 2x is going to give me minus x minus 2, right? So there's another perfectly good solution. You should check, both solutions should be acceptable by default unless they specifically tell you that they want it in one way or another. So it's a little bit up to your author, and so in the homework, just follow the instructions. One or the other should give you the correct answer. Okay. For me on the test, I'm happy with either one. I can see the benefit of either one. You should be prepared to answer either one or just follow the instructions. Okay, so this is the solution that your author provided, exactly the same thing I did, and I'm noticing that your author stopped here. Your author did not expand this, so maybe that's the way your author likes it. Adding and subtracting rational expressions. So now we're going to be working with fractions that fit this form. A over C plus B over C, and we know that they combine to be A plus B over C. So remember that when we're adding fractions, if they have the same denominator, all we do is add the numerators and keep the same denominator. Okay, all right, so hopefully these won't be too bad. Let's look at an example. Okay, so here is an example. We have 3 over x minus 1 plus x over x plus 2. So we're not allowed to do this, right? A very common mistake is for people to just add across and say that this is 3 plus x divided by x minus 1 plus x plus 2, something like that. So we can't just add across. We need a common denominator. So before we actually add it, we're going to have to manipulate these fractions a little bit to get a common denominator. Another common mistake is that people think that we can manipulate just the number part of this term. So people think that to get to an x plus 2, we can add, I'm not sure what they would do, like add 3 here. That gets you to plus 2, so that they add 3 there. So then they get that this is 6 divided by x plus 2, after they add 3 there and add 3 there, over, and then we get an x over x plus 2. And then they go ahead and add the fractions because now they have a common denominator. But we're not allowed to do that, right? The problem is right here, You're not allowed to just add a 3 to the denominator. The only thing we could do is multiply something new into it, right? Not add. Okay, so hopefully that sounds familiar. All right, so we need a common denominator. By default, what you want to do is factor everything as much as possible. These two are already in their most factored form. And then we can easily find the common denominator. In this case, it's just going to be to multiply the two. So we have to take the first fraction, x minus 1, and I'm going to put a little gap there, plus, and then the second fraction, x plus 2. And I'm going to multiply each one of these by a new version of 1. Okay, you're allowed to multiply anything by 1 and it doesn't change it, so we're okay there. And so for the first one, the new version of 1 I'm going to multiply is going to be an x plus 2 divided by an x plus 2. Right? This is a new version of 1. I'm allowed to multiply it by that. And then for the second fraction, x over x plus 2. Again, I'm going to multiply by a new version of 1, which in this case, I'm going to use x minus 1 over x minus 1. Okay, a new version of 1, I'm allowed to do that. Now, when I multiply these fractions, I'll end up with 3 times x plus 2 divided by x minus 1 times x plus 2 plus x times x minus 1 divided by x plus 2 times x minus 1. Okay, so now they have the same denominator. Now we're allowed to combine them. And so this would be one big happy fraction where we have 3 times x. You know what? I'm just going to go ahead. Well, that's fine. I'll expand it next. So this will become 3 times x plus 2 plus x times x minus 1 in the numerator. And now the denominator just has one copy of all that. X minus 1 times x plus 2. Okay, so now we want to simplify this. Let's distribute this and distribute this and that. So we'll end up with 3x plus 6 plus x squared minus x divided by x minus 1 times x plus 2. Combining like terms up in the numerator, we end up with 3x plus, oh, actually, it's reorganizing it. I get an x squared plus 2x plus 6 divided by x minus 1 times x plus 2. Right, so the x squared, I just wrote it out in front. And then a 3x minus x gives me a positive 2x, and then a plus 6. Now we can factor that. We need two numbers to multiply to 6, but add to 2. So thinking about that, 3 and 2 multiply to 6, but that's not going to work. And 1 and 6, that's not going to work. So no, there are no two easy numbers that multiply to 6 to give you a 2. And in particular, we would only really be interested if we can factor it in a way that allows us to cancel one of these denominators. So if x plus 2 happened to be a term, or if x minus 1 happened to be a term, then that could be interesting. But that's not going to work out for any of these. So we're basically done. So now here we have a polynomial form, and here we have a product of binomials. So I think it just looks kind of messy this way. So I would just go ahead and expand out the denominator. And so my final answer would be this one. Put it like this, divided by x squared. X squared plus 2x minus x is going to be plus x minus 2. All right, the second one. Now we have 1 over x minus x squared minus 1 minus 2 over x plus 1 squared. So again, let's go ahead and factor this denominator and see what the common denominator will be. So looking at this fraction, I can see that it'll factor as x plus 1, x minus 1. So this turns into 1 over x plus 1, x minus 1, minus 2 over x plus 1 squared. Okay, so common denominator is going to be to have 2 copies of x plus 1, the binomial, and then one of the x minus 1. So 1 over x plus 1, x minus 1 times, and so I'm going to introduce an extra copy of x plus 1 over x plus 1. That'll give me x plus 1 squared times x minus 1. And then for the second fraction, minus 2 over x plus 1 squared. And we're going to introduce an extra term of the x minus 1. X minus 1 over x minus 1, right? Okay, so now we multiply these, and we get x plus 1 divided by the product of these three. So it's going to be x plus 1 squared times x minus 1 minus 2 times x minus 1 divided by x plus 1 squared times x minus 1. Good. A very common mistake is that people get to this stage and then they start canceling, right? Which is kind of circular thinking. We just went through this work to get to this stage, so why would you cancel them, right? No, we want to notice that now they have the same denominator, so we can bring them together as one big happy fraction, and so we end up with x plus 1 minus 2x minus 1 divided by, and then this is x plus 1 squared x minus 1. Good. So then distribute and combine like terms. So we're going to distribute these guys. Don't forget about the sign. And so we end up with x plus 1 minus 2x plus 2, which then, denominator is still x plus 1 squared times x minus 1. Okay, so we end up with a minus x and a plus 3. So 3 minus x, all over x plus 1 parentheses squared, x minus 1. And again, nothing really reduces. There's no way to cancel one of those, so that's good enough. So here's the whole solution. It's very common for people to do this slightly differently. It's not wrong, it's just more work. So a very common thing for people to do is to just multiply both fractions by the denominator in the other fraction. So for example, instead they would do this, 1 over x squared minus 1, and then they multiply it by x plus 1 squared over x plus 1 squared minus 2 over x plus 1 squared, and then they multiply it. Oh, you know what? Let me keep the green just to match it from over there. So here the new version of 1, the fraction they use here, is this one. So they get x plus 1 parentheses squared over x plus 1 parentheses squared times, and then they use this one, which is x squared minus 1 divided by x squared minus 1. So this method will work. You're just using a term that is bigger than it needs to be. So you just end up working with things that are bigger, and they just end up being a little bit more work. So if you can see a least common denominator, then you'll shave off some of the work you have to do. But if you don't see it, then you could do it this way. This is a common denominator. It's just not the least common denominator. Good. It's kind of like if we just had numbers and we had, to add 1 over 10, plus 1 over 5. The least common denominator is a 10, right? All we have to do is multiply this by 2 over 2, and we're home. Right? You can do 2 over 2, common denominator is 10, and we're there. But if somebody doesn't see that, then by default, you could just multiply by using the value over here. So multiply this by 10 over 10, and multiply this one by 5 over 5. and you'll get to a common denominator, 50, sure, but you're dealing with bigger numbers than you need to. That's all. Okay. So here's the solution your author provided for the first one. Same work we did. And again, notice that they left it this way. They left it as a polynomial in the numerator and a product of binomials in the denominator. And here's the solution your author did for the second one. Okay, compound fractions. A compound fraction is a fraction in which the numerator, the denominator, or both are themselves fractional expressions. For example, we might be asked to simplify something that looks like this. Okay, so when we have something that looks like this, there's a couple ways in which you can approach this. The first way is to kind of think of them as two separate things. Work with the numerator, work with the denominator, right? So just work with this, simplify it, combine it, get it to be a single fraction. Then kind of simultaneously, but separately, work on this denominator by itself. Do whatever you need to do to simplify, cancel, reduce, get to the point where we have a single fraction. So our goal is to rewrite this as some a over b, some fraction, divided by, and then write this as some other c over d fraction. And then we have one fraction divided by another fraction. So we can rewrite this as the first fraction times the reciprocal of the second fraction, which would be a d over c. Okay, so that's our game plan. That's one game plan. And there's another option as well, but let's do it this way first. So, okay, I'll keep that there, and let's copy it over here. So we have x over y plus 1 divided by 1 minus y over x. So focusing just on this fraction alone, I need a common denominator, which is going to be a y. So this one's going to be easy. I'm just going to rewrite this as a y over y. And here I'm going to need an x. I'm going to rewrite this as an x over x, right? Just focusing on this denominator separately from this one, from the numerator. And so now in the numerator, I end up with x plus y divided by y, right? Just focusing on that denominator. And then in the denominator, I end up with x minus y divided by x. So I'm at this stage now. This is a fraction divided by another fraction. So I know I can do this. I can multiply the first fraction times the reciprocal of the second fraction, which is an x over an x minus y. Good. And so we just simply multiply across, and that's x times x plus y divided by y times x minus y. And if something reduced or canceled at this stage, we would do it, but there isn't. Obviously, x and y don't cancel, and these two don't cancel because they're opposite signs. Here we have a plus, here we have a minus. They can't cancel. So we're basically done. You can leave it like this or distribute. Again, it's kind of up to your author to see which style they like. I would be happy with either way. This would be xy minus y squared, right? So just follow the instructions if there's a particular way in which people want it. Otherwise, either one would be fine. So here's our answer. Okay, so this strategy is this one. Deal with them kind of separately and figure it out later. Deal with them kind of separately, rewrite the numerator as a fraction, rewrite the denominator as a fraction, and then use this process to simplify. Here is the solution provided by your author using this technique, right? So again, we just rewrote the numerator as a fraction, rewrote the denominator as a fraction, then we multiplied the numerator times the reciprocal of the denominator and simplified it, right? So again, your author left it this way instead of distributing it. Apparently, that's how your author likes it. Okay, option number 2. So now let's come back up here and let's try something else. I'm going to go ahead and erase all of this. Okay, option number 2. The game plan in this method is going to be to multiply the giant fraction, right? So this ginormous fraction here, we're going to multiply by a new version of 1. Figure out something, a new version of 1, the big fraction right here, this one, we're going to multiply it by a new version of 1, where itself is going to be a fraction. And our goal is going to be to figure out a value such that when I distribute the numerators, that they'll cancel out with any of the smaller fractions that are in the numerator and denominator. Right? So we have to think to ourselves, what eliminates this value here? And so clearly it would be a y, and here it would be an x. So we want to do the following. We want to multiply it by, we have x over y plus 1 divided by 1 minus y over x. And the thing I'm going to multiply the big fraction by is going to be an xy divided by another xy. Remember, we're multiplying the big fraction by this. This is the new version of 1, so we haven't changed anything. We haven't changed the value. And now what we're going to do is we're going to distribute. So we're going to take this term and multiply it times this one times this one, this one times this one, and this one times that one. So we'll end up with an x over y, I'm going to put a little space there, plus 1 times, and then in the denominator, we'll end up with a 1, little space there, minus y over x. And so here we end up with an yx, 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 yx. Right? So each one of these terms gets multiplied by yx. And now is where the fun happens. This y and this y cancel. This x and this x cancel. And what survives is an x times x, or an x squared, and then plus yx divided by, and then a yx, and minus a y squared. So now if we factor out the numerator, there's an x in common. So this becomes x parentheses x plus y divided by, and if we factor out a y, we get a y parentheses x minus y. Good? Okay, so same answer as before. So this is your author's solution using this style, and it's the same thing. We multiply by xy, things simplify and reduce, and so we get the exact same thing. Okay. In some situations, one method works better than the other, depending on exactly what you're working with, but often they're both just as good. So it kind of depends on your own style, which one you like best. I don't really require one method versus another. It's whatever you like, as long as you write down enough work, of course, to be able to follow what you're doing, then either method should be fine. Okay, rationalizing the denominator or the numerator. So we're going to be working with cases that fit this form. So if a fraction has a denominator of the form a plus b times the square root of c, we can rationalize the denominator by multiplying the numerator and denominator by the conjugate rational a minus b square root of c. So notice that if we multiply these two binomials, a plus b square root of c times a minus b square root of c, that this fits the form of this one. If you remember, this fits the form a plus b, a minus b, right? And if we FOIL all this out, get our red claw going, this times this, this times this, this times this, this times this, we get our red FOIL claw going, we end up with a squared minus ab plus ab minus b squared. The middle terms cancel, and so we end up with a squared minus b squared. A squared minus b squared, right? So this is a shortcut pattern. Here, the role of a is a, of course, and b, instead of just b, it's b root c. So we have a case where we have two binomials that are identical in every shape except that one has a plus, one has a minus, just like over here, one has a plus, one has a minus. And so we can conclude that the answer is going to be that this answer is going to fit that form over there. And so we'll have the a squared minus the second term squared, which is b square root of c parentheses squared. And now this is going to be a squared minus b squared, and the square root of c squared is just going to be c. So that's where this comes from. Okay, so that's the advantage of multiplying by its conjugate pair when you see something that fits this form. All right, let's see an example. So rationalize this denominator. Okay, so this fits the form. And so the key to this one is going to be to multiply by a new version of 1, right? And that new version of 1 is going to be to multiply by its conjugate pair, which in this case is going to be 1 minus square root of 2, right? 1 minus square root of 2, 1 plus square root of 2. So these are identical in every way, shape, and form, except one has a plus, one has a minus. Whatever you do to the denominator, you must do to the numerator, so we have to multiply that by 1 minus square root of 2. This is a new version of 1. The numerator and denominator are identical. And now we get the advantage of simplifying the denominator. So now when we simplify this, I'll just put it over here. This becomes 1 times 1 minus square root of 2 in the numerator, divided by, and when we multiply these two, we get 1 squared minus root 2 squared, right? Since this is a difference of squares. Difference of squares gives you this. And so now this simplifies to give me 1 minus root 2 in the numerator. And here in the denominator, we get a 1 from there minus a 2 from there. The square root of 2 squared is just 2. And so this becomes 1 minus root 2 divided by negative 1. And now finally we simplify this by, well, you can think of it in a couple of different ways. You can think of it as separating this into two fractions, 1 over negative 1 minus root 2 over negative 1. So we can kind of think of tucking the negative 1 underneath each one of these, which then gives me a minus 1 plus root 2. Here is your author's solution for this one. And it's pretty much the same thing, except they rewrote this. That's fine. I put minus 1 plus square root of 2, so you can flip it around this way. Okay, avoiding some common errors. So here's this nice little table that kind of provides some common mistakes people make, along with some things that are true. So let's look at this table. Let me zoom in. Okay, so things on the left are correct. They are true. This is how we can simplify these statements. So if you're given a times b parentheses squared, multiplication there, then you can simplify by saying that this is equal to a squared times b squared. But a common mistake people make is that if there's an addition in there, a plus b parentheses squared, very often people think that that's a squared plus b squared, and that's just not true, right? So this is a common mistake you want to avoid. Same thing with roots, or similar with roots. If we have the square root of a times b, we can separate this as the square root of a times the square root of b. This is equal, so you can go in this direction, or you can go backwards. Maybe you start with the square root of a times the square root of b, and maybe you want to tuck it under one big happy root, and so you're allowed to go forwards or backwards with these. Right, so that's true for all of these. You can go in this direction if you want to, or you can go in this direction if you want to. Either way, forwards or backwards, that's what an equal sign does for us. Sometimes we want it in one form, sometimes we want it in another form, but this just is these are the rules of what you're allowed to do. And again, a common mistake is that they translate that to addition, and they're not allowed to do that. So the square root of a plus b does not equal the square root of a plus the square root of b. That's not true. But it is true with multiplication. Okay. Likewise, if we have the square root of a squared times the square root, the square root of a squared times b squared, then the root and the power of 2's do cancel out, and so we just end up with a times b. But that's not true if there's an addition. Again, if we have the square root of a squared plus b squared, we cannot simplify that to be a plus b. Another common mistake. Same thing when we are multiplying fractions. 1 over a times 1 over b does equal 1 over a times b. But again, with addition, we have problems. We need a common denominator, so we're not allowed to just add across this way, right? So this is not true. 1 over a plus 1 over b does not equal 1 over a plus b. Good. In this case, we have a times b divided by a, and that does equal b, right? So here the a's have canceled because there's a multiplication there. Again, a common mistake is people cancel these a's and either put a 1 or a 0. Either way, it's wrong. You're not allowed to cancel the a's in a situation like this. And finally, this notational style, a to the power of -1 times b to the power of -1 does equal to a times b, parentheses, to the power of -1. Remember that a to the -1 power is really 1 over a times, and then b to the -1 power is really 1 over b. And now if we multiply those, again, we don't need common denominators to multiply fractions. This is 1 over ab. And so now this gives you that. It's ab, parentheses, to the power of -1. So this is all true, but this is not true, right? So again, this gives you 1 over a plus 1 over b, and now we need a common denominator. This one would be saying 1 over a plus b, and clearly those are not equal. Okay, so not true. So just some common things to avoid. To verify that the equations on the right column are wrong, simply substitute numbers for a and b and calculate each side. So pick some simple, basic numbers, 2, 3, plug them in, replace the a and b by those values, and confirm for yourself that the rule just doesn't make sense. So for instance, if we look at the fourth error in the list of common errors, and we let a equal to 2, b equal to 2, and replace both sides of that statement, on the left-hand side, we would get 1/2 plus 1/2. 1/2 plus 1/2 is equal to 1 all day long. And then on the other side, the right side, if we replace the a and b with 2's, we end up with 1 over 2 plus 2, which is 1/4. So clearly, 1 does not equal 1/4. So that should help confirm for us that 1 over a plus 1 over b does not equal to 1 over a plus b. Okay? All right, so you can do the same thing with the other ones and kind of convince yourself that they make sense. And if you're in the middle of a test and you're not really sure, this is a nice strategy in general. Just try a few simple little numbers and confirm for yourself if you're allowed to do something. Are you allowed to simplify it this way? Are you allowed to cancel? Are you allowed to rewrite it this way? So it's just a nice little strategy that works sometimes. Okay, so hopefully you have enough to work on your homework. As usual, if you have any questions, feel free to drop by my office or my office hours.